Hi, and welcome to this video where we're going to continue our look at complex numbers. So the complex numbers are defined in Python using the complex class, so that's the data type, and you can always look at help on the complex class. It's built in. We don't have to import anything in this case, unlike the decimals, for example. And so we have the constructor. So the constructor just takes the real and imaginary parts. So in other words, complex numbers by default use rectangular coordinates. So we can say maybe 1, 2. And then we can also use a literal way of creating complex numbers, which is 1, the real part, plus 2, and then we use the letter J for the imaginary part. And J can be either lowercase or uppercase. It doesn't matter. I'll just use lowercase here. And of course, we can compare those two numbers. They should be the same. And we get true. Now, we'll come back to the equals because it's true in this case, but it's not always true in general. And we'll see why when we look at how to retrieve the real and imaginary parts of a complex number. So let's look at A or B, and let's see how we would return the real part of A. We just say A.real, so it's an instance property. At the same time, let's take a look at what the type is of A.real. And as you can see, we get 1.0 back, and it's a float. Now, we did define 1 as an integer, but complex numbers have their real and imaginary parts stored as floats. So we're going to have the same approximation problems that we saw with floats with complex numbers, except now we'll have it in both the real and imaginary parts. So we'll circle back to that. Let's first look at how we would get the imaginary part of a number, of a complex number. And we can look at the type as well, just to make sure. But as you can see, we get 2.0, and it is also a float. So we're going to have to be careful there. We also have the instance property called conjugate, which gives us the complex conjugate of the number. So we can look at A.conjugate. It's a method, not a property. And it returns 1 minus 2j, which is the complex conjugate of 1 plus 2j. Now, we also have the standard arithmetic operators that we can use. So plus, minus, division, and so on works as one would expect with complex numbers. So let's say we have A equals 1 plus 2j. And let's say we say B equals, I'll make them different, 10 plus, let's say, 8j. Okay. And now we can print A plus B. We get 11 plus 10j. We can do A times B, etc. A divided by B, and so on. So we have all these possibilities, these standard arithmetic operators. We could also have powers, so we can say A squared, for example, which will give us minus 3 plus 4j, and so on. So the standard arithmetic operators work just as expected. Now, the ones that don't work are the div and mod operators. They are not defined for complex numbers. So if I try and say A div 2, we get this error here. It can't take the floor of a complex number. What does that have to do with the div? Well, remember when we looked at how the div operator was defined for floats, it was a floor division. And essentially that's what's happening here. So that doesn't work. And of course, neither will mod. That doesn't work either. So we can't mod complex numbers. And of course, the div mod function isn't going to work either since, well, we can't have div or mod. They're not implemented. And neither will the div mod function as well. Okay, so let's take a look back very quickly now at the equals, which is supported, as well as the not equals. So that's supported for complex numbers, but we have the same caveats that we have with floats. So as an example, let's say A is equal to 0.1j. Okay, so let's define that. I'm not going to define a real part for A, so the real part will be 0. Let's just focus on 0.1j. It's still a complex number. And let's take a look at A. Well, let's go ahead and format A.imaginary in this case. Okay. And let's go out to 25 digits after the decimal point. And as you can see, we do not have exactly 0.1. It's this binary float representation issue that we've discussed before. So we can do the same thing here. We can look at A plus A plus A. Now that should be equal to 0.3j. So we might want to test and say, is that equal to 0.3j? And the response to that would be false, right? And that's because if we were to format, let's format each one of those. So let's say A plus A plus A. Now I'm going to take the imaginary part of that, and then we're going to look at, so that's the value, and then we're going to format, and we're going to take 0.3j dot imaginary, also at 25 digits after the decimal point, and as you can see, they're not exactly equal to each other, right? We have this finite binary approximation, so that's why the equals equals doesn't work. So we'll circle back to that and see how to fix it, but essentially it's going to be the same way that we fixed it in floats, the same approach that we took in floats, using, you know, a measure of how close two numbers are to each other to define whether we consider them equal or not. So we'll come back to that. So the next thing that I want to look at is the CMath library. Now, when you're dealing with floats, you have the math library, right? So we can import math. Right, that's our standard math library. We can say math.square root of 2. That gives us that. We have math.pi, right, which returns pi up to a certain number of course, finite representation of pi. Now, the CMath library is very similar, except it's defined for complex numbers. So CMath has, you know, most of the functions that you find in the math library, like square root and exponents and sines, you know, all the trig functions, the hyperbolic functions, all those are in there, as well as the arc functions. So let's take a look at some of those. Let's start with pi. Pi is also built in to the CMath library, and it gives us that. And let's look at the type. Is that maybe a complex number? Does the pi that comes from the complex module give us a complex number? And the answer is no. Essentially, the pi that we have in the CMath module and the pi that we have in the math module are the same thing. It's there as a convenience, so that if you're working with complex numbers, you don't have to import the math library, the math module, just to get pi, right? Because the functions that you have in the math module will not work on complex numbers. So if we have, let's say, a equals 1 plus 2j, right? If we try and do math.square root of a, well, that doesn't work, right? It can't convert a complex to a float. Complex has these two parts, right? It's more like a vector if you're talking about rectangular coordinates than a single number. So you can't do that. You have to use the CMath square root, which will then give you the complex square root. And same thing with the other, you know, functions that are available in the CMath library. They're specifically made for complex numbers. So you can't use the math library in general for that. Okay, so in the math library, some other functions that might be of interest is how to convert from rectangular to polar coordinates. So by default, complex numbers are stored as rectangular coordinates using floats for the real imaginary parts, but very often we want to work with polar coordinates with complex numbers. So we can take a complex number in rectangular and get the angle, the phase, or the argument of the complex number using the CMath.phase method. So let's take one where we might actually know the phase. Let's say we take a complex number equal to 1 plus 1j, right? So we know that this is a complex number which is at a 45-degree angle to the real axis, and it should have a length, you know, an r value of square root of 2. It's just the Euclidean distance. So if we say CMath.phase of a, it gives us this value here. And in fact, if we say CMath.pi divided by 4, we'll see that that's approximately the same thing. So that's how we get the angle when we go from rectangular to polar. How do we get the Euclidean distance? Well, it's just the absolute method, and it's the absolute function. It's not in the math or the CMath library. We're not using the CMath float absolute, the FABS. It's just the plain absolute method, which is just built into Python, and it will work with complex numbers. It's polymorphic, and it will handle complex numbers correctly. You just pass that in, and you'll essentially get the Euclidean norm. You'll get that r value, which is 1.414, which is what we expected, square root of 2. So that's how you can go from rectangular to polar. Now, how do we go from polar to rectangular? Well, we have that in the CMath module, there is a function called rect, and that takes two parameters. It takes the r and the phi. So it takes the r value. Let's say we're going to take one. Well, I'm going to do this. I'm going to say take math.square root of 2. I'm going to try and get as close as I can. Okay. And then for the angle, I want a pi over 4. So we're going to say math.pi divided by 4. And let's see what we get. Well, we get 1 plus 1j. Now, it's not exactly 1 plus 1j. You know, again, I mean, first of all, square root of 2 is not going to have a finite representation, not even in decimal. And same thing with pi. Pi doesn't have a finite representation, and therefore neither does pi over 4. But we're close enough. We can see we're very close to 1 plus 1j. So that's how you can convert from polar to rectangular coordinates using the rect function in the CMath module. All right, lastly, I want to talk about Euler's identity, and we again discussed that in the slides. So let's go ahead and just write out what it is. So this is what it is, e to the I pi. I is kind of more standard notation in complex numbers in math, but in Python they use j. So this would be e pi j, e to the pi j plus 1 equals 0. So let's go ahead and test this equation out. So the right-hand side, it's equal to, well, we have to use the exponent. So the exponential function is done using the exp function in the CMath module. So what do we want to take the exponent of, the exponential of? Well, we want I pi. So we want CMath or math.pi, doesn't matter, times 1j, right? We want to make it into a pure imaginary number. That's one way of doing it. Alternatively, if you want, you could just say complex 0, comma, math.pi. That would also work the same way, where we have 0 plus I pi, right, essentially. So we can do it that way as well. And then plus 1. And let's see what we get. So let's go ahead and print right-hand side. And as you can see, we don't exactly have 0. So it kind of spoils the nicety of this equation, but it's very close to 0. It's not exactly 0, but as you can see, 10 to the negative 16 over here, right? Now, we can therefore try and see, well, is it close enough to 0? Just the same way we did with floats. And we're going to use the isClose function. Now, we can't use the isClose function that's in the math module, but there is one available, fortunately for us, in the CMath module. So we can go ahead and say cmath.isClose, and we can take right-hand side, which we just calculated, and 0. And if we do that, we're going to get false. Why? Why are we getting false? It's really close, right? This number here is really close to 0. Well, if you remember our discussion on floats, that's precisely the problem, right? This is using a default relative and absolute tolerance, right? If we look at help on cmath.isClose, you'll see that it has this relative and absolute tolerance concept as well. And by default, the absolute tolerance is 0. And the relative tolerance is 10 to the negative 9. And remember that we had discussed that before, but if you're comparing numbers that are very close to 0, then the relative tolerance really doesn't work anymore, and you have to then fall back to an absolute tolerance. So the moral of the story is the same as with floats. We have to make sure that we specify absolute tolerances as well. So let's go ahead and do that. And we'll leave the relative tolerance as is, but we'll override and provide a specific value for the absolute tolerance that will not be 0. And let's say 0.0001, for example. And now when we do that, we get finally that, yes, the right-hand side is close enough, according to this tolerance, to 0. All right, thanks for watching, and I'll see you in the next video.